Let's say we're given some surface using the multivariable functions. Before we discuss how we can find the volumes under the surfaces using the double integration, or how we can find the area of the surfaces using the double integration as well. So in this video, we would like to discuss how we can find the area under the surface along some curves. So let's say we're given some curve C, and I would like to make a wall or fence until the surface, and I would like to find its area. The concept of finding this area is very much similar to everything what we did before. So let's say we're given some curve on the xy line C, and we would like to cut the surface along this curve, and we would like to find its area. In order to do this, we would divide this curve into as many small pieces where the length of each of the pieces would be delta s. And in order to find this area, for example, I would just multiply the delta s to the height of this rectangle, and the height of this rectangle could be found by evaluating the function at this point, x1 and y1, let's say. And then the next area would be ds multiplied to the f of xt, yt. And in general, I could find the area of the rectangle, or this piece, by multiplying the delta s to the f of xi in yi. And if I just sum this, where ai goes from 1 to the n, it would give me roughly the area. And if I take its limit when n goes to the infinity, it gives me exactly the area. And I can define this using the line integration of the surface f of x and y with respect to the arc lengths along some curve C. More precisely, if this curve is given using some parametric equation x is equal to h of t and y is equal to g of t, then we could evaluate the ds as taking the derivative from the x with respect to the t, dx dt and a square, plus taking the derivative of the y with respect to the t, dy dt and a square, taking the square root and multiply this to the dt. And we can just substitute this into here in this formula of the line integration. So let's do a small example how it works technically. We would like to find the area under the surface along the curve C, which is the upper half of a unit circle. Basically, I would like to choose a upper half of the unit circle. Then I would like to cut this until the surface, and I would like to find its area. Let's look to this circle along. So we are given a circle, a unit circle with a radius 1, and we could write down the circle using the parametric equation. X would be equal to the r cosine of t, where the t would be the parameter, the angle, right? So they were starting from this point, and this is our t, the angle between the x line and our points. And y would be given as the r sine of t. So since the radius of the circle is equal to the 1, we could just write down x is equal to the cosine of t, and y is equal to the sine of t. Then the line integration of a surface along this curve C would be equal to the integration of the surface, which is given with the equation t plus x squared y multiplied to the square root of dx dt plus dy dt in the squares, taking the square root and take this integration with respect to the t, where the t is going to change from 0 until pi, right? So the angles are going to change between 0 angle until pi angle. So in order to simplify this, let's substitute the dx dt here. So dx dt would be equal to the minus sine of t, and dy dt would be equal to the cosine of t. So if I take its square and add this to the square of the dy dt, it would be simply equal to the 1, since it is sine square plus cosine square of t. And I could substitute the x and y with the cosine and sine, and what I get is the integration from 0 to the pi t plus cosine square of t multiplied to the sine of t and we need to integrate this with respect to the t. So the integration of the first part is very much straightforward. So if you would integrate this separately, it would be the integration from 0 to the t of the t with respect to the t. Its antiderivative is t. If you substitute then 0 and pi, if you substitute the 0 and pi, you would get simply t pi. The integration of the second part is slightly difficult, but we can use the substitution rule. So the integration of the cosine square of t sine of t dt, we could use the substitution. U would be equal to the cosine square of t, and du would be equal, cosine of t, and du would be equal to the minus sine of t dt. So in this case, our integration becomes, so sine of t dt is minus du, and we can take this out, this minus out of the integration, and cosine square of t is simply u squared, and its antiderivative would be minus u cubed over 3, and we can resubstitute this back with the cosine. It would be minus cosine cube of t over 3, and we can evaluate this from 0 until the pi. If I would substitute the pi, it would be minus 1, so t pi minus 1 over 3 minus 1 over 3. With this minus, it is plus, so this is going to be t pi plus t over 3.